Hi, in this video we're going to look at the dot product. We're going to start with looking at a physics example of the dot product so you can see why we might want to do something like the dot product. Then we're going to look into some theoretical examples of how to calculate it. So I'm going to start with a couple of terms that we're going to look at later in the series: displacement and force. So the definitions we're going to use for this video is displacement is distance but with a direction. So I could travel 3 meters, that's a distance. If I travel 3 meters in the north direction, that is a displacement because it has direction. Things with a magnitude, 3 meters, and a direction are vectors. So displacement is a vector quantity, whereas distance is just a scalar quantity. The second one here is force. What we're going to use for this video is an influence capable of changing an object's velocity. So for instance, if I was to push someone, their velocity may change. So when I'm pushing them, I'm applying a force to them. If they fell 30 centimeters in the south direction, they would have some displacement in which they are moving. So with that said, we're going to have a look at this example here. We've got a toy car moving on a horizontal surface and it's moving in a direction. So I've got that indicated on the diagram. Now it might be moving at 2 meters per second, some velocity. If I was to apply a force to that car, so if I'm going to apply a force to the car behind it, and I'm going to apply it for a certain distance that the car is traveling. So let's say that I apply 10 newtons, and the numbers don't really matter for the example, but we'll just put them here anyway. And I apply it over 2 meters in that direction. What's that going to do to the car? If I'm applying a force to it, it's going to speed the car up. So it's going to increase the car's energy. If I apply the force over 2 meters, it's going to speed the car up a certain amount. It's going to apply that, increase the energy by a certain amount. If I was to apply the same force, but I was to apply it as the car moved 4 meters, then I'm going to increase the energy of the car. I'm going to double the energy increase that I put on the car. If instead of applying it over 4 meters, if I was to apply the force over 2 meters, but I was to apply double the force, so this blue arrow represents a 20 newtons force, then again, I'm going to double the energy I'm putting into that car. So what we can see here is what matters about the change in energy of that car is, and let me write that here, change in energy equals the magnitude of the force matters. So I'm going to call that force. It's a vector. Matters what direction we're applying it in. We've got the magnitude of the force times by the magnitude of the displacement. And that tells me what my change in energy is going to be. Now, this is a physics context. I'm not going to go into the derivation of that formula, but this is just use an example to help us understand why dot product is important. Now, if I was to apply that same 10 Newton of force, but instead of applying it horizontally like in this example, what if I was to apply it on an angle like this? So this is going to be 10 Newtons as well, at some angle here. And the car is still moving in the same direction. It's bound by the ground, so it can't move down. It's always going to move in that horizontal direction. Is this blue force going to impart as much energy onto the car as the black force? Well, the answer is no, because some of the force is being wasted by pushing it into the ground in a direction it can't move. All that matters in terms of the energy that we're putting into the car is the horizontal component of that force. Now this should look very familiar because this arrow that I've drawn is the vector projection, but what we're looking at because we're looking at magnitudes over here, we're just looking at the scalar projection because all that matters is the overall size of it. So when I'm looking at the change of energy, if I want to incorporate the angles into things, my formula is going to break down into this. What matters is the force, or the scalar projection of the force in the direction of the displacement, in the direction that the car is moving. And we're going to multiply that by the direction or the magnitude of the direction in which it's moving. Okay, or the magnitude of the distance in which it's moving, sorry. So this is going to be our change of energy here. Now let's look at some implications of this. If we were applying a force that was directly down on the car, okay, so in this example we're not considering friction. So if we were to put a force directly down on the car, instinctually you might think it would stop, but that's because of frictional forces. If we're putting a force directly down, we're not changing at all the force that's going in the left and right direction. So the car would continue at the same speed. So that means we're not changing the energy of the car at all. If we look at the angle between these two vectors, the force vector and the displacement vector, if we look at that angle, it's 90 degrees. If I put that 90 degrees into my formula, cos 90 is 0, so we get 0 times the magnitude of the force times the magnitude of the displacement. 0 times that is just going to be 0, so we get no change in energy. If we were to do a force that was pointing in the opposite direction of motion, then you can see that we're going to be slowing down the car. And as it turns out, any of my cos thetas, if theta is in between 90 and 180 degrees, is going to give me a negative number. So what that'll mean is I get a negative energy change because we're slowing the car down. So this quantity here, or this formula, sort of gives us some idea about the change in energy of the car. It's also the formula for the dot product of two vectors. So if I had the vector f and I had the vector d and I do the dot product of those, this is how I calculate it. And what it does is it gives us an example, or it gives us some quantity about how much things are pointing in the same direction as each other. In this particular example, it tells us how much of a change of energy is this toy car going to have. So let's go through some examples of how we can calculate it for a range of vectors. So let's have two vectors like this. Let's say the magnitude of A is 5. And let's say the angle is 50 degrees between them. So what we're looking at is the dot product between these vectors is the magnitude of A times by cosine of the angle between them times by the magnitude of B, where this first part here is just the scalar projection of A onto B. So if I draw that in here, we're looking for this length. That gives us my orange part here. And then we're multiplying it by the magnitude, by that length. So if I enter in my values, we've got 5, 5 cos 50 gives me 3.21. So this length here is 3.21. We're timesing it by 6, and we end up with 19.28. And that is what the dot product of those vectors are. If I was to do another pair of vectors, let's do one like this, where this is 90 degrees. So C dot D, 10 cosine 90 times 2. Cosine of 90 is 0, which equals 0. So we have a dot product of 0, and what this implies is the scalar projection of one vector onto the other vector is 0, right? Here there was some overlap between the vectors. Here there is 0 overlap in direction in which they're pointing, so we don't get, our dot product is just 0. Let's do another example. So in this example, let's have vectors pointing in different directions. So let's go sort of opposite directions like this. I have E and F. And let's say there's 170 degrees between them. So writing out the formula here, we've got E cos theta by F. So what we're looking at is the scalar projection of E on F. So if we extend the line out like this, we are looking to find what this length is here. That's what this component tells us, and that's our scalar projection of E onto F. So we've got 10 cosine of 170 by 5. So we get negative 9.84 is this length. Again, it's negative because it's not overlapping the F vector, it's in the opposite direction. We are timesing that by 5, and we get negative 49.24. What happens here if we do F dot E? So let's have a look at the other order. So I'll do that down here. If we did F dot E, we are doing magnitude of F cos theta by the magnitude of E. Now, intuitively, this should give me the same result, because what I have is 3 numbers all times by each other. It shouldn't matter if I put them in different orders. I should get the same result at the end of it. So let's go ahead and look and develop the intuition behind that. So in this case, we are finding F cos theta first, which is the projection of F onto E. So we've got this length here. So that's going to be 5 cosine 170, and then we're going to multiply that by 10. Negative 4.92 times 10. Now look at the scalar projection here and the scalar projection here. You can see the one we've calculated down here is exactly half of this one. And this is 2 times this. Now half times 2 just equals 1, so we should end up with the same product when we multiply these two together that we did up here. And if we do it, we will find that we get negative 49.24. So what that means is if you have any two vectors, let's say u dot v, that is also going to equal v dot u. Okay, so in summary, before I do a summary, the last thing that I wanted to say is This is typically not the way that the dot product is written. Normally it's written with the E and the F together. So normally it's written like this. Oh, we don't have those here. So we have E dot F equals E F cos theta. Now this is great for implementing in terms of just typing numbers into a calculator, because you can just put all of these terms at the front and then do the angle at the end, and that's completely fine, and that's how I input it when I'm doing the problems. However, when you're getting a geometric intuition for what's going on, I recommend that you view it in this way. You are getting the scalar projection of one vector onto the other, and then you're multiplying that by the length of the other vector, because that's effectively what the dot product is. One last point I'd like to make about dot product is to try and estimate it before you do it. So I'll give you an example. We had and this angle was, I don't know, 65 degrees. So what I mean by estimating it is I want you to visualize how long this line is going to be here. So looking at that, if everything's drawn properly, I'd say it's maybe 2 or maybe 1.5 maybe, that length. And then 1.5 times 6 is going to be 9. So I'm going to estimate that A dot B is going to be 9 in this case. The reason why estimation is a really valuable tool in this is because it forces you to get a geometric view of what's happening before you solve the problem. And I keep harping on about this geometric intuition of these problems. Why is it important? Because one, it gives you a good conceptual understanding of what's going on. Number two is because when you go out into the real world and you're actually solving problems, someone doesn't ask you to use the dot product to do this. You've got some real world scenario and you have to use the tools in your mathematical toolkit to solve problems. Now, the way that you might do that in a vectors case is you might visualize some real life examples as vectors. And then by getting that geometric picture in your head, maybe the dot product is the best way to calculate what you want to or to get you where you need to go. But without that visual intuition, that geometric intuition, it's going to be very, very difficult for you to sort of perform those calculations in terms of what calculations do you need to do in the first place. So I can't stress it enough. Geometric intuition and visualizing these problems is super important. One, for your studies here, but two, for actually utilizing these studies outside of the classroom. So that's dot product. I hope you enjoyed the video, and I'll see you for the next one. This video accompanies a worksheet series that aims to develop conceptual understanding with vectors. If you'd like to access the worksheet, click in the description below.